is Caroline Adcock. I am a meteorologist here at the National Weather Service office in Nashville, and I'll be giving tonight's presentation about satellites. So if you guys are here right now, then you probably have heard about our Weather 101 series, and this is just a way for us to be able to be with you guys and let you know about different meteorological features, different tools we use, and lots of different things like that. While our office here in Nashville was the original ones to start this, we actually have a lot of presentations from other offices as well. We do offer it to everyone across the U.S., so I would love to know where you guys are located tonight. If you guys want to just say what state you're from or what city, either in the questions or chat box, it would just be really cool to see where everybody's listening in from tonight. So in this class, we're going to be going over satellites and just some of the background and history of satellites, as well as some of the products and applications. So I wish I could go over a ton of stuff about satellites, and people in college these days take entire semesters worth of classes just covering satellites. But unfortunately, I only have an hour with you guys tonight, so we'll be primarily focusing on our GOES 16 and 17 satellites that we're currently using. So kind of going over the background and history, we're going to just talk about what satellites are and how they work, some of the limitations and advantages, and also just advancements in satellite and how we've gotten to where we are today. And like I said before, we'll be primarily covering GOES 16 and 17, which are the satellites we use the most here right now, and then also just some real-world applications. So what are satellites? So satellites, generally speaking, are just the study of the Earth's atmosphere and atmospheric processes using measurements from satellites in orbit. So here on the right, I actually have an image from one of our GOES satellites. This is our GOES East satellite and our GeoColor, which I'll go over later. But newsflash, this is actually not what the satellite is sending us down here in space. It looks really pretty, and it is kind of what the satellite's showing us, but not completely what the satellite is showing us. So these are indirect measurements. You guys might have heard of things called remote sensing. Satellites do fall under the class of remote sensing just because this isn't an exact picture. A lot of times people think satellites, oh, it's just a picture down on the Earth. And while that can be the case, it's actually not the case with our GOES satellites. So typically the orbit of the satellite influences what the satellite is able to tell us. So things like how fast the satellite travels or also where it orbits are really important in the information that we're able to get. So just going over a brief kind of timeline of how we got to where we are today, and just looking at satellites in general. So the first satellite that was able to go up into space was in October of 1957, and it was Sputnik 1. And this was actually a USSR satellite, and a lot of people don't realize, but this was actually a precursor to the space race. So a lot of you guys hear about the 60s and trying to get the first man on the moon, which we did, but the USSR actually got 2 satellites into space before we were able to. So we had our first try in December of 1957 with Vanguard 1. Unfortunately, it was not a successful attempt. But we did have our first successful release in January of 1958 with Explorer 1. So that was our first U.S. satellite to make it to space. By March, we were able to get some more technology on our satellites, and we had 2 failures between then. But something that's actually really cool is that March 1958 Vanguard 1C satellite is actually still in orbit today. So it's not sending any data. We have no idea what it's doing, but we do know that it's still orbiting Earth and is still actually in space. So it is the oldest orbiting satellite right now. So looking at weather satellites, so the first satellites that went to space kind of were more just tests, got a couple images, but weren't used for meteorology. By October of 1959, that was the first satellite that had some weather-related instruments on it. And then by 1960 is when we had the first satellite that was purely dedicated to meteorological studies. By 1966 is when we had our first geostationary satellite, which the word geostationary refers to where it is in orbit, which I'll go over here in a minute. But it was actually intended to be a communication satellite, but ultimately was used for weather. And then in 1975 was actually when our first GOES satellite was in orbit and when the GOES program for NOAA began. So we're going to watch a short video here that kind of goes over two of the bigger types of satellites that we use here, and also just how we work with other nations as well.
NOAA operates three types of satellite systems for the United States: polar orbiting satellites, geostationary satellites, and a deep space satellite. Polar orbiting satellites circle the Earth and provide global information from 540 miles above the surface. Geostationary satellites constantly monitor the Western Hemisphere, 22,240 miles above the Earth. And our deep space satellite orbits 1 million miles from Earth, providing space weather alerts and forecasts, while also monitoring the amount of solar energy absorbed by Earth every day. While NOAA operates many satellites, no one country alone can afford to effectively monitor the entire Earth. NOAA partners with the international community to leverage data from satellites around the world, providing a more complete understanding of our ever-changing planet.
So while we do have satellites in orbit, we aren't the only ones. And we do rely heavily on some other country satellites. I know later I'll talk about that we partner with Japan and their Himawari satellites.
NOAA operates three types of satellites.
There we go. So the two satellites that I'm going to kind of just briefly touch on are POES and GOES satellites. So as you saw in the video, we do have a POES satellite, which is a polar orbiting environmental satellite. So what this does is it usually will orbit around the poles, and it provides more high resolution snapshots. But as you can see, it is kind of lapsing in some coverage. So we have these gaps, and since it's constantly rotating around the Earth, we're not able to get a 24-hour view over one area. The first satellite that was that we used weather instruments on in April of 1960 was a POES satellite. But nowadays, we still do have POES satellites in orbit and use them a lot. But something that we'll use more often, I know we will use more often here at our office, are the GOES satellites. So GOES stands for Geostationary Operational Environmental Satellites. So these satellites orbit above the Earth, above the equator at the same speed as the Earth rotates. So where the POES will orbit around the Earth here, GOES satellites will basically mirror the Earth and follow the Earth in rotation, so we're actually getting a look at the Earth 24/7 from the same location. And the first GOES satellite was launched in October of 1975. They're also located much further away than our POES satellites, which kind of contribute to why we have a better picture of things with the POES. They're closer to the Earth, so they have a higher resolution just in what we can see, whereas the GOES satellites are further away. So we're going to have our first question. Trust me, it's not anything hard. But our first question here is going to be, what was the name of the first American satellite to make it to orbit? So the first satellite in general to orbit was Sputnik. However, that was not an American satellite. So it actually looks like we have 42% for both the Explorer and the Vanguard satellite, but it was the Explorer 1 that was the first American satellite. The Vanguard 1 is still in orbit today, but the Explorer 1 was our first satellite that made it to space. So if we're moving forward here, let me see. So whenever we talk about geostationary satellites, this is the program that we're using most often today. So since 1975, GOES has provided continuous imagery and data of atmospheric conditions and solar activity, so space weather, things like that. So our first GOES 1 through 3 were in the 70s. By the 80s, we launched 3 more satellites. By the 90s, we had 4 more. And as each step went forward, we were able to provide different data and able to, our technology just kept getting better and better. You guys are stuck on the quiz. Okay, let's see here. Never had this happen before. Let's see if we can get it to change now. Okay, can you guys see that now? I've never had it get stuck on the pole before, so. Okay, perfect, good. So this is what I was just talking about. So in 1970s, we had our first satellites. These were spin stabilized satellites, which isn't what we use today. Started getting some more information in the 80s. By the 90s is when we first started getting simultaneous imaging, and we actually got some soundings. And then in the early 2000s, we had GOES 13, 14, and 15, which 14 and 50 are actually still in orbit today, and we do use somewhat today. And then now we have the GOES R series, which honestly was a great jump for the field of meteorology. We have a lot more data coming from these satellites and get a lot more information. So you guys might be wondering how we get these to space. So NASA actually builds these satellites for us, and then we'll launch them, and then NOAA will take over and operate them. So kind of what I was talking about before, here's a list of all of our GOES satellites. So starting with GOES A or GOES 1 was in October of 1975, and it was decommissioned in the 80s. And if we keep going down, you can see we did have some failures. I know we had one fall out of orbit, so that just basically means it did not get to where we needed it to be, and we just weren't able to use it. So going down to where we are today, so GOES 14 and 15 are actually still in orbit, but right now we're focusing on this GOES R, S, T, and U. And so that's also known as GOES 16 and 17. GOES 16 was launched in November of 2016. GOES 17 was launched in March of 2018. They do cover different areas. So GOES 16 is more the eastern U.S., whereas GOES 17 is the western U.S. If you guys are wondering when the next launch will be, we're actually scheduled to have a launch of our newest satellite in December of this year. And then we'll have another satellite in 2025. So looking where we are today, we're up here in 2021. So we actually do have 4 satellites that are kind of in orbit that we use. So we have an on-orbit spare. We have 2 on-orbit spares from 14 and 15. GOES 14 is actually used basically in the middle of 16 and 17 if something were to happen, whereas 15 is being used as storage. So looking over the coverage areas, so like I said, GOES East is centered further to the east over the eastern U.S., and then GOES West is located actually over near Hawaii, and showcases a lot of the western U.S. here. And then our standby satellite, GOES 14, is kind of in the middle of the two, so that if something were to happen to GOES East or GOES West, we do still have coverage from this other satellite. But I will say the advancements between GOES 16 and GOES 17 are so much greater than what GOES 14 had, so we really hope that that wouldn't happen. So covering how satellites actually work. Again, I could go days on days talking to you guys about how satellites work, but from a very basic perspective, we use 2 different areas of the visible electromagnetic spectrum. So here we use mainly visible light as well as infrared, and both of those just give us a different picture of what is going on in the atmosphere and what we can actually tell from this. So I'll show you guys some examples earlier, and you might be seeing some of this and it might not make sense, but it will make sense when you see the pictures. So each channel measures the amount of reflected or emitted energy at a specific wavelength. So when I'm talking about reflection, it's just like if you guys see something reflecting from a mirror. So if we have the visible spectrum, which are some of our channels are in the visible spectrum, they are dependent on sunlight. So just like you and I, we can't really see at nighttime. It's super dark. If it's pitch black, we don't see anything. So that's how it is with the visible spectrum for some of the channels on our satellite. So reflected energy and means that those bands are only available during the daytime. Whereas emitted energy is where the energy is giving off, and it's kind of can be related to temperature, but those are in the infrared spectrum. And since it's emitted energy, it's available during both the daytime and the nighttime. So like I said, the visible channels, they're the sunlight reflected off the earth, and we can only see in the daytime, whereas our infrared channels we're able to see both at daytime and during the night. So how do we get this energy to Earth? And I want you guys to notice we have a pretty color here with a bunch of different colors, but then our image over here is black and white. And actually all of our images that come from the GOES satellite are black and white. So anything you see later that has color, that color has been added after the fact. So whenever the satellite, it will scan the Earth and it will create a full disk of data. Once it gets this information, it will send it down to the Earth. Since we have to use computers to understand this data, it will code it into a binary code, so zeros and ones. This is why we can't get any color information. It's just black, white, yes, no. So once the computer translates this code into pixels, that's how we get our image. So you guys will see here in a minute, our visible spectrum will be black and white, and that's just because that's the data that we're receiving. We're not getting any type of actual picture seeing colors. You guys might notice this picture here, we have color, and that's because it's been added after the fact. So here we're able to use different combinations of different wavelengths, and that's how we're able to paint this pretty picture of what the Earth probably looks like, and we can pretty much confirm from the ISS or different things like that of what the Earth looks like, so we know this is a pretty close representation. But this picture right here isn't actually what the satellite is sending us, or the satellite is actually sending us a picture more like this. So the GOES R series, there's this bunch of different instruments that are on board, and just in the purpose of time, I'm really going to only cover two of them today. So we have two Earth pointing instruments. We have the Advanced Baseline Imager, or ABI, and then we have the Geostationary Lightning Mapper, or GLM. We do have two sun pointing instruments, and then also some other instruments that we'll use, some for space and some for here on Earth. But today we're going to focus on these two because these are the two that we use most often in meteorology. So the Advanced Baseline Imager is a multi-channel passive imaging radiometer that images Earth's weather, oceans, environment with 16 spectral bands. By spectral bands, this goes back to that electromagnetic spectrum I was showing you earlier. All of these bands are located at different locations in the electromagnetic spectrum. Some of them are in the visible, some of them are in the near infrared, and then some of them are in the infrared. And just each of these shows us something different about what's going on at Earth. The geographic coverage, so for the full disk, we'll get a circular image that's depicting nearly full coverage of the Western Hemisphere. So in GOES 16, we'll see a lot of the East Coast, and that actually even expands to the West Coast. But then on our GOES West, we'll see more of the Pacific Ocean. We also have a CONUS and PACUS view. So CONUS obviously is with our GOES 16, GOES East, and then the PACUS, so over Hawaii and the Pacific Ocean, is GOES 17. Something that's really cool with our GOES 16 and 17 satellites is we do actually have a mesoscale coverage area that is movable. So it's a smaller rectangular image with a higher temporal resolution. Temporal resolution just has to do with time. So generally speaking, our full disk in our CONUS we get every 5 minutes, whereas the mesoscale we actually get an image every minute, which is just really incredible that we're able to get images that quickly. And we have two of those on board our GOES satellite. So it is movable. If there's any type of severe weather, usually we'll move it there. Or whenever we have hurricanes, we'll usually move the mesoscale sectors over that area. And requests can be made. So I know a few weeks ago when we had all of our severe weather here, which is some of the real world applications I'll use later, we actually had a mesoscale band over our area here in Middle Tennessee. So the other tool we'll talk about just briefly is the Geostationary Lightning Mapper. So this is just a single channel and it's a near infrared. Basically, it's just taking a bunch of pictures and noticing if there's any type of lightning in that image. So it allows us to get a continuous view of where lightning is located, and it measures in cloud to cloud, and also cloud to ground lightning. A lot of times it'll tell us things such as frequency, the location, and the extent of the lightning. And this is really useful for us in identifying thunderstorms and also tropical cyclones. So typically speaking, it helps us get an increase in tornado and other severe storm warnings. A lot of times right before a storm is going to get potentially more violent, we'll see an uptick in lightning. So it helps us with that. It also helps us with detection of heavy rainfall and flash flooding, and also improved aviation routes. So if you're in a plane, you don't want to fly through a thunderstorm, but knowing exactly where the lightning is located is very helpful. So our second question here is, how many GOES ABI bands are there? So it looks like most of you guys are getting the right answer here. It is in fact 16. So there are 16 GOES bands that we utilize. So moving forward, we're going to start talking about some of these ABI bands. So everything that I'll go over here is both true for our 16 and 17, our GOES East, West, and East. So the first band that we have is known as our blue visible band. And what this means, it's actually located in the electromagnetic spectrum of the color blue. And so this will be the image that's here in the top left. And I actually have a bigger image on the next slide that we can dive into what each of these are showing us a little bit more in detail. So we have our blue band up here, our red visible band here, which all that is, it's very similar to the blue band, except it's located in the red visible spectrum. And because of this, we actually get a little bit of a crisper image. Down into our third band is the veggie band. We start moving out of the visible band and into the near IR. So we're still getting visible characteristics here, but as you can see, the image is a little more dull, but it actually shows us a little bit different information. And then by band 4, our Sirius band, again in the near IR, it's a little bit further down the spectrum, but just shows us different information. So if we blow this up, we have our blue, our red, our veggie band, and our Sirius band. So our blue and red image, generally speaking, show us similar information. A lot of times we're able to deduce where clouds are located, snow's located, different things like that. And especially when you animate images, you're able to deal with different characteristics here. So if we take a look over Colorado in both of these images, you can notice there's some white features here, but nothing is moving. So if you guys know anything about snow and that it's March in Colorado, this is more than likely snow over the Rocky Mountains. Whereas if you look down here in Florida, this white imagery is moving, so these are most likely clouds. So we just have a crisper image here on our visible satellite versus the blue. But we can tell a lot of things from this. So we can see that there's snow through the Rocky Mountains here. We have clouds, some low-level and mid-level clouds here, which you might be wondering how I can tell that there's both. So some of these clouds are moving over other clouds. So that's showing us that there's clouds at different levels going on here. You guys might also notice off the coast of California that we have this counterclockwise rotation. That would actually be a low pressure that's moving into California given this date and time. The gray area over the rest of the U.S., most of this during this day, we actually had high pressure over the area, so we didn't have a lot of clouds around the area. If we look at the veggie band, it's short for our vegetative band. So here is where a lot of times it'll show us where there's a lot of vegetation. So if you guys aren't familiar with eastern Arkansas and into western Mississippi, this is actually the Mississippi Delta, and it's located on the Mississippi River, and there's a lot of agriculture through this area. So you don't really see that on our visible bands, but into this different part of the electromagnetic spectrum, we're able to see where vegetation is located. So you can see all these little spots. Those are probably where there's densely located vegetation. Into our cirrus band, so cirrus meaning cirrus clouds. These are our high-level clouds. When we look at the visible band here, you can see there's clouds, but you do have a little bit of difficulty knowing where they are. Whereas when you look at this band, you can really tell, hey, all of the stuff that is here are higher clouds. So if we compare these two, all of these off the East Coast are higher clouds, but you don't really see any clouds over the Gulf of Mexico, and that's because those are lower level clouds. So they're not being picked up on this band. Moving into our next four bands, we have the snow and ice band. Similar to the veggie band, this helps us deduce where snow and ice is located because they're actually these darker colors here, and that just has to do with how the energy is emitted. We also have cloud particle size, the shortwave window. So this is still, it actually is moving into the IR part of our spectrum by this band. But the really cool thing about this band is it has different characteristics during the daytime and nighttime. So as the sun's going up, you can see that there's more vibrant colors, and that's because this daytime is actually helping to reflect more energy. So we're kind of picking up on that still. But it's still, we're able to use it during the nighttime. So it is a very unique band that way. And then band 8 is our water vapor, which we actually have 3 different water vapor bands. The next 2 I'll cover on the next set of slides after this. But looking over the U.S., if you guys remember earlier, we had a bunch of snow located on the Rockies, and we can see that there's this darker color here. You guys might not have noticed, but on that earlier slide, we had a bunch of clouds over Minnesota and Wisconsin. So it was hard to tell if there was snow on the ground, but looking at this, we can tell that there actually was some snow on the ground up here. Our cloud particle size, some of these bands I won't go over as much because we don't use them individually. We'll use them for some products that we're able to do some really cool stuff with that I'll go over later. Again, our shortwave IR, so here our darker colors, so our reds and things like that, mean that it's typically warmer versus these cooler colors are cooler. So as you move up in the atmosphere, it typically gets colder. I hope you guys knew that, but if you didn't, spoiler alert. So off the coast of California, remember how we saw all those cirrus clouds? They're super high in the atmosphere, and a lot of them are ice particles. And because of this, we're getting this cold emitted energy, and which is why they're showing up in these blue colors. But then across the rest of the U.S., we didn't have any clouds. It was a pretty warm day. So we're seeing all this red showing up across the U.S. This band over here, band 8, is our upper level water vapor. And so here we have dry air, these reds and blacks. And then we have more moisture in the greens and the blues, which upper level water vapor, generally speaking, we don't see a lot of dry air in the upper levels. We do see more of it as you move down in levels. And using upper level, mid-level, and low level, and I'll show the upper and mid, the lower and mid here in a minute. But using those 3 bands, kind of subtracting them from each other or looking at different things gives us an idea of where troughs and ridges are located. So it's kind of difficult to see here in this image. You can still see the rotation of the low pressure here, but you guys will really start to see it when we move into our mid-level and low-level water vapor here. So we have our mid-level water vapor and our upper-level water vapor. So these, those should say IR. They're not near IR. They are part of the IR spectrum here. Pretty much every band, every channel from here on out is part of the IR spectrum. So we have mid-level tropospheric water vapor here, low level here, cloud top phase, and the ozone band. So these 2, band 11 and 12, are 2 bands that on a day-to-day basis here at our office we don't particularly use, but they are utilized by different meteorologists looking at different things. It also can be utilized looking at our RGB products, which I'll cover those here in a minute. So looking a little bit closer, we really start to see that low pressure off of California in the counterclockwise rotation. We see all this dry air coming in and a lot of moisture through California here. And then a lot more moisture here off of the East Coast. And it looks like that we have probably the remnants of what was a low pressure here. So there's a little bit of counterclockwise rotation, but it's mostly falling apart. So you can see it's mostly dry across the U.S., which when we looked back at the visible band to start, it was dry. There weren't any clouds over the U.S. And then these two bands, like I said, can be utilized in some different ways, but we're not going to cover them individually. The last four bands, again, are this one, the clean IR window is used a lot in meteorology. If you guys see images of hurricanes, 9 times out of 10, it's going to be the clean IR window. Which this is actually slightly different than what was on our previous satellites, and this gives us a more crisp image, and it's just really good to utilize, especially in tropical cyclones. So band 14 is another version of our IR window, so this is just further down the electromagnetic spectrum. Again, band 15, same thing, just further down the spectrum. And then band 16 is actually very interesting because it actually shows us some CO2 levels and how we can infer that. Bands 14, 15, and 16 are utilized in some of our RGB products that I'll cover here in a minute, so I won't go over them individually. But I do want to talk about this clean IR window that's up here. I have some really cool images that you'll get to see here in a minute that will show you how we can utilize this during severe weather or even tropical systems. But here what this is doing is it's telling us the emitted energy. So over these darker images, it's kind of an inverse of what you're thinking. So these darker images, these grays and whites, those are actually warmer temperatures. So here at the surface, it's obviously warmer. Our dark or our higher colors here, so our reds and our yellows over here, and some of these greens and blues, those are actually colder emitted temperatures. So as you move up higher in the atmosphere, you're going to get even colder temperatures. So what's that showing us is a lot of times where strong storms are located. So I'll go ahead and move forward here. But this is actually from our March 17th event. So we didn't get a whole lot up here in Middle Tennessee on that day, but especially down in Alabama and some in Mississippi, there were a lot of strong thunderstorms and even some really bad tornadoes in Alabama. So this here is our GOES band. So that day, like I mentioned earlier, we had a mesoscale sector, and it was actually a big enough day. We had both of the sectors located over the southeastern U.S. So we had one of them located over Arkansas, and the other one was just to the east. So it was giving us a better picture of what was going on, and we were able to monitor this with getting 1-minute imagery, which is why you can see all this information. So just going over some of the things that if I was working on that day and saw this, just things I could tell you guys. So one thing, looking over here in Oklahoma, you can see there's a little bit of this counterclockwise rotation. So that is more than likely where our low pressure was located on that day. We have this clearing here through Texas and Oklahoma, and then eventually into Arkansas. More than likely, our front that was kind of initiating some of these storms was probably back here through this area. You might notice there's this bubbling going on through Mississippi and especially in Alabama. That's actually robust updrafts from these thunderstorms moving through this area. So a lot of times when we have these very strong thunderstorms, we'll get very strong updrafts. They're basically making like popcorn in the atmosphere, and they're bubbling up to the top of the atmosphere. Where we see this bubbling is more than likely where some of the strongest storms were located. I know down here in Alabama, there were a couple of strong, long-track tornadoes, and we can definitely tell that there definitely was a robust updraft. It isn't a one-to-one thing here. You guys can see there's some strong updrafts here in northern Mississippi, but those actually didn't produce a ton of strong storms. So we can't just look at satellite imagery and say right there is where something's going on, but it does help us infer and give us a first place to look. So if I was looking at this day, I could definitely tell that there was probably some very strong storms here through eastern Mississippi and then into Alabama. And you can see this going on here on this image. I do want to show you on this image, you can see really well. Sometimes in meteorology, we'll talk about shear. If you've never heard of shear, all it is when wind is going in a different direction. So a lot of times in meteorology, if we have very high shear, that's a lot of times when we'll get strong storms. So tornadoes, severe thunderstorms, things like that. So looking at this imagery here, you can tell some of these clouds are moving in an east-west motion. But then if you look down here in the Gulf of Mexico, we actually have this north-south motion. So since these winds are going in different directions, that's actually showing us that we're having some shear here. So we're having this north-south motion and east-west motion. And if we look closely here in South Alabama, you can see these clouds are going under these other clouds. So higher motion is going east-west, whereas our low-level motion is more north-south. So that's just something that just looking at satellite imagery, we're able to draw all these different conclusions. So looking a little bit more, so again, this is our visible GOES band, and then over here is our shortwave band. So remember I said earlier the shortwave band has characteristics that are both in the visible spectrum and also in the IR spectrum. So these colors, we're getting this information kind of from the IR spectrum, but as you see as this image is going on, the surface of the country is actually getting lighter, and that's because this image was taken as the sun setting. You can definitely tell it in this visible spectrum. So since we're not getting as many of the sun's rays, the earth is cooling, which is why we're getting a lighter gray color here. But looking at this band, you can see again where some of those stronger storms are located. Where these blue colors are all located, those are more than likely ice particles and high-level clouds. So especially here where some of these clouds were bubbling earlier, those are really strong storms. Back here into Arkansas, some strong storms, but some of it's actually cirrus clouds here. You can really see cirrus clouds up in the Boot Hill, Missouri. In a second, you can see that's where these ice particles are located. Moving into water vapor like we talked about earlier. So right here, we're looking at our upper level water vapor, our mid-level water vapor, and our low-level water vapor. So the low-level water vapor, you can see this dry air that's moving into Arkansas. And as you remember earlier, we didn't have a lot of clouds on the visible spectrum there. But as you can see over Mississippi and Alabama, we have these really dark green colors, and that's where some of our stronger storms were located. And then we have pretty much dry conditions through Florida, and then as we move up into the mid and upper levels, we start to get more saturated. So as I talked about earlier, this is our clean IR window, which this is a really good way of noticing where those strong updrafts are. So where we saw those bubbling clouds earlier, you can see that we have these reds and oranges and yellows. That means that those are probably higher cloud tops than some of the other clouds in this area. That's where we have the coldest cloud tops, where there's some ice particles. So those are probably some very strong storms with some really robust updrafts going on. And as you can see, the thing that's interesting is our cirrus clouds, you don't really pick up on those reds and yellows. You really only see those with those strong storms. And I wouldn't leave you guys without a hurricane, so I did want to show you guys Hurricane Maria. So if we're over the ocean, we unfortunately don't have radar data. As it was moving through Puerto Rico, we had some radar data, but really the way we're able to track storms through the tropics is from satellites. So looking at GOES 16, this was as Hurricane Maria was making landfall, and this is that channel 13 that I was talking about, that clean IR window. So we see here that we have some really warm colors. So we have some blacks and reds, oranges and yellows, and that's actually because that's how that's helping us deduce where some of those strongest updrafts are in the coldest cloud temperatures, which is just showing us strength, generally speaking. You can see some of these cirrus clouds coming off here. Those are the whites and the blues. But we can also see the eye of the hurricane on this IR, because if you guys know anything about hurricanes, in the center here in the eye, it's usually calm and we don't have a lot of clouds going on, which is why it does show up on our IR band. Whereas the most intense part of a hurricane is generally right outside of the eye. And you see that right as it's making landfall, that those blacks are located right around the eye. And that's where more of the catastrophic damage was located. So some additional features here that I had briefly mentioned earlier and we'll go into a little bit more in depth are RGB products. So RGB stands for red, green, and blue. And all this is that we're able to combine different channels that I just showed you to highlight the presence and evolution of different things that are going on. So things like fog, dust, this is utilized a lot in fire weather, snow and ice, and also air mass. We're able to get all this information just from assigning values to like a red color, a green color, or a blue color. So a lot of times we'll use 2 or more bands, and then sometimes we'll subtract them, sometimes we'll just compare them, but we're able to get a different image here. So this is actually GOES East viewing a fire that was in California. So if we looked at the visible spectrum, we wouldn't necessarily see this. But being able to utilize RGB, we're able to clearly see where this fire is located. So just all the different RGB products, I wish I could cover them all today. I'll go over a few so you guys can see a little bit more. The image down here is my personal favorite RGB product, which is the Airmass RGB product. But we see things like dust, air mass, ash, fire temperature. We have a day snow fog, a day cloud convection, nighttime microphysics, which I utilize a lot. I know a lot of meteorologists will utilize this. Differential water vapor, dayland cloud fire, lots of different things that we can utilize comparing different bands here. So one example is the day cloud phase distinction. So here on the right, we have an image of our visible water or our visible band. So it's just gray. You see a lot of white. So there's a lot going on. You don't know, since it's not animated in this picture, we don't know if it's cloud, snow cover, really what's going on in this picture. But if we add the day cloud distinction, so here we utilize the clean long wave infrared. So as I mentioned earlier, that gives us some information about the how the brightness, temperature, and how cold the cloud tops are. We're also able to see things. We utilize the red visible band and then also that snow and ice band. And it just gives us a better understanding and able to differentiate between different weather phenomena. So here on the right, can't really tell what's going on. But here on the left, we get this really pretty picture and are able to determine exactly what's going on. So knowing what the colors are, which all of these do have quick guides that I can give the website to at the end of this presentation. But they tell you kind of different things what's going on. So we're able to see, there's water clouds up here, snow cover located over here in the Dakotas, some more water cloud, ice clouds are in this color, and then the bare surface down here in these blue colors. So it's a lot easier to know what's going on in this image than is in this image, and we're able to utilize different bands to give us that information. So I mentioned earlier the nighttime microphysics. So again, we'll use 2 versions of our long wave here. We'll use the clean and the dirty, which just basically provides us with some more information about how clouds are acting. So if they're thin or they're thick. We'll also utilize the clean infrared again, and then we'll look at the short wave, and that gives an idea if it's ice particles or water particles. And then the blue color again is that long wave IR to give us some temperature information. So looking here, we have some high thick clouds over the Dakotas and into Colorado and Wyoming. Here we have this low cool cloud. But then you might be seeing some of these colors that are the same, but you can tell there's just subtle differences here to let us know where the warm clouds are located and very low clouds, but also where the fog is located. So we do have some fog here that's this dull aqua color here into Arkansas and Oklahoma and Texas. But like I said earlier, if we were to look at this imagery from space, obviously the visible band, we can't utilize at nighttime. It's in the visible band. So at nighttime, we're really relying on our IR channels, which can be difficult to deduce fog just looking at the IR channels. But if we start assigning values to them, we get this much prettier picture. So like I mentioned earlier, we have an Airmass RGB, which is my personal favorite. And this will actually tell us where air masses are located, which is really helpful in knowing just where these air masses are, where they're going against each other. This can give us some frontal information and different things like that. So here in the southeast U.S., we're by the Gulf of Mexico. It's very moist down here. So we have a warm and moist air mass here in the southeastern U.S. As you start moving up into the northeastern U.S. And into the Rockies some, that's where you start getting more mid-level clouds and also some cooler air. And then you can just tell there's a lot of warm air down here. Since this band does utilize some of that clean IR window that we talked about earlier, it does pick up on where there's high clouds. So here we have some high, thick clouds. Probably looking over here, just with the way the clouds are going, it looks like we probably have low pressures over the mid or upper Midwest here, and then also off the coast of New Jersey here. This is another example and just a real-world application of how we recently used one of these products. So here we're looking at the dust RGB product. So here we can see this magenta color that's representing our dust, and then we have some cold and thick clouds over Colorado, and also some mid-level clouds, and just a lot of things going on. This was actually back in March when Colorado had a very big snowstorm. And something that was really interesting is that the National Weather Service in Boulder actually was able to show where there was a layer of dust in their snow. So this was a picture that was taken where you see this white, all the snow, but you see this very thin layer of brown. And that's actually where some of this dust that was shown on our dust RGB product was making its way all the way up into Colorado. So GOES 16 in action. So this goes back to that March 17 date we talked about earlier. I did want to talk about what I had mentioned earlier, that some of our RGB products do rely on the visible spectrum. So for example, here on the right, this is or on the left, pardon me, this is our day cloud phase. As you can tell, the sun is more than likely setting in this image because we're losing the vibrant colors. And that's because one of the colors in this band actually relies on the visible spectrum. So once the sun goes down, we're no longer able to use that. Here on the right is our sandwich, which just utilizes it does utilize some visible spectrum components, but has a lot of IR components. So we're able to see those robust big storms again. So that's where these reds and yellows are located. If you remember our visible band that we saw earlier, some of those stronger storms were located through here. So one of the final ones I want to talk about was going back to that first image we looked at, which was our GeoColor. So the GeoColor, like I said, it's not an actual picture that the satellite is just sending us. It looks beautiful, but we're actually assigning all of these colors. So during the daytime, we use a combination of some of our visible bands, so our blue band, our red band, and our veggie band. But then we're also utilizing some data from the Himawari satellite I was using earlier. So our channels, we have that blue band, which is in that blue visible spectrum, and a red band, but we actually don't have a technical green band. But the Himawari satellite, which is a Japanese satellite, does. So we use some of that data to help us assign some of these colors. So this image I actually took, it's from today. So we can see this was last night. During the nighttime, we'll utilize the long wave infrared that GOES 13, that channel 13, and also some of our fog products, which utilizes some of that near IR. They actually use a database of where all the cities are located and just some of the lighting in those cities. That is a stationary thing. So if the power goes out, let's say in Atlanta, you're not going to see it on this image. It's a static image underneath. But we're able to get this pretty picture here. And as you can see also, you guys might see this bright dot, and we'll watch it come back around here in a second. So we have daytime. We have this bright object going over the equator, and you really start to see it as it moves to the western hemisphere. and then it goes to, the sun is starting to set. I took this image about an hour before this presentation, so at that time, the sun had already set, obviously, over Africa and was making its way to the U.S. That bright spot that we see as it moves across, that's actually the sun. So sometimes if you look really closely, we won't see it really up here in the U.S. because the sun's never located over our area, but since it's located over the equator, we're able to pick it up really nicely on the full disk. So I wanted to touch briefly on that GLM product that I had talked about earlier, and that's our Geostationary Lightning Mapper. This again is from today. We had some storms in Arkansas and as well in Louisiana and Texas. And these yellows and greens and reds, this is basically all of the lightning activity that was going on in these storms. So we can see the most activity are these reds and kind of purpley colors with some less colors going on elsewhere. And like I had mentioned at the beginning, this is very useful for us to just know kind of where storms are developing because this does give us data about some in-cloud lightning. So some of our lightning detection networks only will take data that's a cloud-to-ground lightning, but a lot of times before we get cloud-to-ground lightning, we'll get inter-cloud or cloud-to-cloud lightning. So if we're able to know where the lightning is ticking up, that can provide us with some information of where some of our stronger storms are located. So some benefits and applications, kind of like we talked about today and wrapping everything up, we have improved hurricane track and intensity forecasts. We're able to utilize things like our visible band as well as our infrared band, that channel 13, to know where hurricanes are located and what's going on. We can also get some increased thunderstorm and tornado lead time. Sometimes if we see that uptick in lightning, that can tell us that that storm is picking up strength and can kind of tell us to look in that area. We can also get some earlier warning of lightning and ground strikes that way, and we can get some better detection of heavy rainfall. But generally speaking, there's a lot of different applications that we're able to use these GOES satellites for. They're located a lot with fire weather, so fire weather detection and intensity and location. I know a lot of our IMEDs out in the western U.S. and even some in the plains will utilize the GOES satellites to be able to know where the fires are going on and also the intensity of them. We're able to see some low clouds, fogs, and just a lot of different things that way. So some more advantages and disadvantages. So an advantage of the GOES satellite, and this is something that's just with the GOES satellite, is since it's a geostationary satellite, it's always located in the same spot and can view the entire Earth at once. So we are always seeing that same exact full disk that I showed you guys a minute ago. That is what our GOES East is always showing. It's never going to change. We have a very high temporal resolution. So like I mentioned earlier, we get a scan every 5 minutes, and then the mesoscale, we get a scan every minute. And it can be very useful for severe weather and nowcasting. Some of the limitations to the GOES satellites is that our visible channels, obviously, we can only use during the daytime. So while they're great to be able to use during the daytime, we can't use them during the nighttime. So some of our RGB products that are really good, we're unfortunately not able to use once the sun goes down. Also, since it's located over 22,000 miles from Earth, the spatial resolution is not exactly the best. So while you can see the general area of where it's located, you're not going to be able to see, hey, this lightning strike is located right over this exact house. It gives us more of a pixelation, so we know a general area, but not an exact location. Polar orbiting satellites, like we mentioned previously, those POES satellites, they do have a higher spatial resolution. Something you may have noticed on some of the images, as you move towards the poles, because of the Earth's curvature, we actually do have some limitation and some issues because of that. So our final question for the day . And Looks like most of you guys have answered correctly. So all of the above are advantages. So we get an increased severe weather monitoring and nowcasting. Those infrared channels, like I said, they're available 24/7, which can provide us with a lot of information. And we do have a very high temporal resolution, which is just really good for us to be able to utilize. So with that, our next Weather 101 will be covering the wind, and it's actually tomorrow night. So if that's something that interests you, be sure to go and register for that class. And I'll go ahead and open up to questions. I know I do have a couple of questions that came in during the presentation that I'll answer briefly right now. One of the questions was talking about Alabama and the shear I was mentioning earlier. What I was talking about earlier when I said the north-south motion, it was a south to north motion. I was just showing, just generally speaking, we had two different planes of motion. We had that west to east motion and then that south to north. So what you mentioned there was correct. And it did kind of, I know the radar does show a little bit different than satellites. The radar, you have to remember, is looking at basically, it's very low to the ground versus satellites. Looking at our satellite images, that's a top down, whereas our radars are more bottom up. So looking at a top-down image, you're going to see some different things than what a radar can use. And that's where satellites, in terms of issuing warnings, we won't be using a satellite for issuing tornado warnings, but it can provide us with some information of where storms are strengthening or a general idea of their location. I know here when we had some tornadoes a couple weeks ago in Middle Tennessee, we actually saw that uptick in the lightning right before it produced a tornado. And our meteorologists that were warning at the time noticed that trend and were able to hone in on that storm. And then as soon as it started showing rotation, we were able to issue that warning. So some websites for information, honestly, if you just go to Google and Google GOES satellites, you'll see a lot of stuff from NOAA and also NESDIS. NESDIS is who kind of monitors our satellites. There's different universities that have even more information. I know Colorado State has a really good website that has a lot of information on satellites, as well as the University of Wisconsin. They'll have quick guides, and a lot of that is kind of what I talked about today, but if you're wanting to get some more information that way, that's some really good things. Another question I saw was about the low Earth satellites, so Starlink. Do those interfere with the GOES satellite imaging? No, it actually doesn't, just because of the pixeling of the satellites and how far away they are. We know where all of them are located at a certain time, so it doesn't actually interfere with anything that way. So if you guys have any other questions, feel free to ask them either in the chat function or the questions box. Are keys available somewhere to help us with the RGB products? Yes. So I know the University of Wisconsin, there is a web page that has quick guides. So if you